So every calculus exam ever probably has a question on it, take the derivative from first principles or from the limit definition. So what they mean from the limit definition is the derivative of a function with respect to x, df dx, is equal to the limit of this expression. The limit is h approaches 0 of f of x plus h minus f of x all divided by h. And there's three types of this question. There's three main types of this question. Polynomial, functions with a polynomial, functions with a root sign, and functions with a fraction. So I've got sort of three basic examples. Let's go over the techniques, the strategies for solving each one of these three types. Before we jump into that though, let's just look for a second at this limit definition, what they really mean by that. I'm going to draw my axes, my x-axis, my y-axis, and I'm just going to draw some kind of function here. So this is f at x. And we want to get the derivative of that function at, let's say this x value. And so we're going to take a second point. I'm going to take this x value, move over h, so this should be x plus h. This is the point here. That's the point x, f at x. We get the y value by just plugging the x into the function. So that's that point. What I want the derivative. I want the slope. The derivative is the tangent slope formula. So I want the slope of the graph at that point, just the slope of the line at one point. But the slope formula that we know before we know derivatives is the is the secant slope formula, the slope of 2 points. So there's one point, x, f at x. Here's another point, which is the x value is x plus h, and the y value is, so this point is, the x value is x plus h, and the y value is, stick the x value in the function, f of x plus h. So the slope between those 2 points is a secant line, a slope between 2 points, and that's rise over run. So the slope, and I'm going to use m for slope, that's rise over run. Now the rise is, the end y value is f of x plus h, so f of x plus h, and the starting y value is f at x. So it starts here and goes to here. It looks like my line was flat, but you might write this as y2 minus y1. That's our rise value. The run is just how far over did we move on the x-axis. That's h, but we could set it up like you would normally set it up, x2 minus x1, and then those x's cancel out. So f of x plus h minus f of x all divided by h. This is the secant slope. That's the m. That's the slope between 2 points. That's the slope between these 2 points. I'm locking down this point. I'm locking down the first point, the x, f at x. And I'm taking this other point and I'm moving it. I'm shrinking x down. I'm taking the limit as h goes to 0. So I'm shrinking that value down, shrinking h down, so that this point moving along the curve, pushing those 2 points closer and closer together so that the secant slope becomes the tangent slope. So let me draw a better picture. Just blow that up a bit. That's what I want for secant slope. There's a tangent slope. If I move that closer, there's another tangent slope. If I move that closer, that's practically the same slope. So as h approaches 0, this value squishes onto that x value. That means this f at x value squishes on. So these 2 points squish together and the secant slope becomes the tangent slope, the derivative. That's what I want. So that's why this is our definition of the derivative. It's the tangent slope formula, and the derivative is the tangent slope formula. All right. How does that help us here with our 3 types? Our 3 main types are polynomial, something with a square root sign in it, and something with a fraction. Let's look at our polynomial type first. So what I'm going to do is, I'm still going to start with our definition here. So each one of those three types, I'm going to start with my definition. I'm going to do the polynomial first. So f at x is x squared plus 2x. So f at, I don't know, f at q would be q squared plus 2q. F at whatever is whatever squared plus 2x. So this f at x plus h here, what I want to do is I want to take this function, there's f at x, and everywhere there's an x, exactly everywhere where there's an x, I want to put a x plus h. So everywhere there's an x, I want to put an x plus h. Everywhere there's an x, I want to put an x plus h. A common error here is people just put 2x and they tack on a plus h. It's got to be in the brackets. I would just mechanically use the brackets if I were you, especially on a test. And f at x, well, here's our f at x, just a regular function. I'm about to just replace this, sub this in for f at x. Oh, but that's going to be wrong because we're subtracting the whole thing. So throw some brackets around that. So there's my f at x plus h. Everywhere there was an x, I put an x plus h. There's my f at x. I'm remembering to subtract the whole thing. And now I've got my limit definition set up for this particular polynomial function. The strategy for a polynomial is just going to be expand everything. Let's take a look at, before we jump into the three main strategies. Our function here, why we can't just make h equal to 0. If I do, I'll be dividing by 0, and the top will also be 0, f of x minus f at x. So the definition is set up so that it's a 0 over 0. So we have to do some algebra before I can make h equal to 0. And it's the h equal to 0 on the bottom in the denominator that's the problem. That's the one I want to cancel out. So all three of these strategies are designed so that I can get an h that factors out of the top, and then I can cancel the h that factors out of the top with the h on the bottom, and then it's safe to make h equal to 0. Okay, let's take this, and I have to be careful. I haven't taken the limit yet, so I have to still write limit as h approaches 0 each time until I actually make h equal to 0. So I'm going to multiply this 2 through the bracket, so that'll be 2x plus 2h, so 2x plus 2h. I'm going to multiply this minus sign through that bracket, so it's minus x squared minus 2x. I can already see that this plus 2x and this minus 2x here are going to cancel. Let's leave that till the end though. I'm now going to square this bracket out. So if I square this bracket out, it's going to be x squared plus 2xh plus h squared when I square that bracket out. So the polynomial strategy is just expand everything. Now I'm going to do some canceling, and after I do canceling on the top, every piece that's left over should have an h on it, so I can factor that h out and cancel it with the h on the bottom. So this x squared doesn't have an h on it, so it should cancel. Oh, it does. That x squared cancels with this minus x squared here. This 2x doesn't have an h on it, so it should cancel. It does. That plus 2x cancels with that minus 2x. Now every piece on the top has an h attached to it, so I can factor that h out. So that h comes out, one of these h's comes out, and that h comes out. I wanted to factor that h out because now I can cancel this h on the top with this h on the bottom. That leaves me with a 1 on the bottom, canceling that h at the top. Now it's safe to make h equal to 0. So when I make h equal to 0, I'm getting 2x plus 2. And that's the derivative. Yeah, if I would have went back here and just differentiated this the regular way, using power rule, I would have got 2x plus 2. So you can always check your work here. So the take-home message, polynomial, you expand, factor out the h, cancel with the h on the bottom. Let's look at this root sign next time, this next one. I'm going to still throw down the definition. I'm going to start with the definition. But in this case, my function is root 3 minus x. So I'm replacing this f at x with root 3 minus x. I'm going to replace this f at x plus h with root 3 minus f at x plus h. But remember that x plus h has to go in exactly where that x is. So I threw brackets around it. That's replacing this x with bracket x plus h. The strategy for, so I can't make h equal to 0. The strategy for this is to multiply by the conjugate. So take your root sign piece, and the conjugate just means switch the sign. It was a minus there, so switch it to a plus and make the top and the bottom the same. So this piece that I'm multiplying by, if I cancel top and bottom, that's just 1. So I'm essentially multiplying by 1. I'm not changing anything. I'm just changing the way it looks. What I'm doing is exploiting the difference of squares. Remember, difference of squares, if you have a squared minus b squared, if you have a squared minus b squared, that should factor into a minus b times a plus b. I'm just going to use this backwards then. I've got a minus b times a plus b. The a is the one with the h in it, the b is the one without the h in it. So it's going to equal to this piece squared minus this piece squared. And by squaring, I get rid of the big square root signs. So equals. Now I still need to write down limit. I'm getting this piece squared, so it gets rid of the big square root sign. This piece squared, so it gets rid of the big square root sign. But I got to be careful. That's minus the whole thing. I didn't need brackets around this one because it was a plus. And this piece on the bottom here, it's just going to be multiplied by the h. Remember, my strategy, just like it was in the polynomial case, is I want an h to factor out of the top here so I can cancel with that h on the bottom. So now let's clean this up here. I'm going to take this bracket off, so it's going to be minus 3 plus x. I'm going to take this bracket off, so it's going to be minus x minus h. And now this 3 cancels with this minus 3. This minus x cancels with this plus x. And the only thing left on the top is minus h. So now that h on the top can cancel with that h on the bottom. With that h on the bottom gone, it's now safe for me to make h equal to 0. So I don't have to write limit. I'm just going to take the limit. I'm going to make h equal to 0. So that just gets rid of it. Now, we can clean this up. I will clean this up. But this is technically the answer. But look, it's root 3 minus x plus another root 3 minus x. That's just 2 of them. So there's my answer. Now, if I would have went back here to this root sign 1 and wrote it as 3 minus x, instead of square root, if I went to the power of 1/2 and then did chain rule on it, I would get the same answer using the easy way. But they wanted us to do limit definition of the derivative. Okay, this one more one more example is if there's a fraction. But I start the same way. I take the limit definition and I need to replace those functions with my specific function that has a 1 over x plus 2. So f of x is 1 over x plus 2. So I'm replacing this f at x with that 1 over x plus 2. I'm replacing this f of x plus h. Everywhere there's an x, I'm going to put an x plus h. Now I don't need the brackets around this one. Good practice would be to put the brackets in, but in this case they don't do anything, so I'm just going to get rid of them. But I'm thinking about it. Okay, it's this h on the bottom that I want to get rid of. Our strategy now is going to be common denominator these two fractions together. The common denominator is the two bottoms multiplied together. So I'm going to multiply top and bottom of this fraction by x plus 2, x plus 2. Again, I'm just multiplying by 1. And the other fraction, top and bottom, I'm going to multiply by x plus h plus 2 over x plus h plus 2. So in both cases, multiplying by 1. But that's going to give me a common denominator of x plus h plus 2 times x plus 2. So let's clean this up. I haven't taken the limit yet, so I still need to write limit. I'm multiplying fractions, so it's going to be top times top. Let's multiply the bottom times the bottom here for that, cleaning up those pieces. The denominator of the second fraction is going to be the same. Well, yeah, because that's what we wanted. We wanted it to be a common denominator. And 1 times there. So now they're common denominator. I can add those two pieces together. When I do that, though, it's minus times all of these pieces. So it's going to be when I put them together, a minus x, a minus h, and a minus 2. So from this step to this step, I common denominated them together. Now, remember, it's this h on the bottom. So what I want to do is I want to be able to factor out an h, cancel an h here. So notice that this minus x cancels this positive x. This positive 2 cancels this negative 2. And I'm left with minus h on the top. Now this looks a little funny sometimes to people. I'm going to try and improve it by thinking about that h on the bottom as h over 1. Now I'm going to invert and multiply this h over 1. So instead of dividing by h over 1, it's like multiplying by 1 over h. Sometimes that's a little bit easier to see that now I can cancel this h on the top with this h on the bottom. Now that h in the bottom is gone, it's safe for me to make the h's equal to 0. So when I make this h equal to 0, that's going to be x plus 2 times x plus 2. So our full answer is minus 1 over x plus 2 squared. So I stopped writing limit because I actually took the limit. I made h equal to 0. Go back up to your question, and if I would have thought of this as x plus 2 to the power of minus 1 and then did chain rule, the minus 1 comes down, subtract 1 from the exponent, I would have got the same answer. So those are your three main types of take the limit definition of the derivative. If it's a polynomial, expand and cancel that h on the bottom. If it's a root sign, multiply by the conjugate, cancel that h on the bottom. If it's a fraction, common denominator it together, cancel that h on the bottom. It's all about getting rid of that h on the bottom. Oh, and in the end, after you get your answer, check by regular differentiation so you know you got the right answer.